And that day, all of a sudden, power cut has happened at my place, so I couldn't extend it more. Just give me a minute. Let me start with the content. That day already we have learned about this isothermal reversible expansion, right? I'll just reverse it once and then we'll move forward. Yeah, this chapter is very, very important with respect to JEE and NEET. Okay, so basic concepts need to be clear. So what would be the work done in isothermal reversible expansion that can be calculated with respect to what? Integration in the limit, negative integration in the limit V1 to V2, that is P extensive into dV. dV is nothing but a change into volume. Okay. Yes or no? And when it will be for the ideal gas, that time what? P extensive is nothing but what? nRT upon V. This one. That need to be, keep it in your mind. Is equal to what? nRT upon V. And only just that value has been placed at the place of P extensive. Right? And the constant term has been taken out of the integration, that minus sign, N, R, and T. Where T would be the temperature, R is the gas constant, and N would be the number of particles. So V1, V2 limit, that would be dV upon V. Okay, and the limit is what? V1 to V2. And because of that, you will get the value of isothermal reversible expansions work done is equal to what? Minus nRT ln V2 upon V1. Why we have written V2 upon V1? Because our limit is in between V1 to V2. So the higher limit would become up and the lower would go down. Okay. And what would be the dV? It is an infinitesimal or very, very small. Very, very small change in temperature. Sorry. Change in volume, not temperature. Understood? Yes. And when there would be the dt is nothing but very, very small change into time. Then dP means very, very small change into pressure. These things you need to keep it in your mind. Okay? Yes, Dhananjay?
Yes, ma'am.
Fine. Shall I erase it?
Yes, ma'am, you can erase it.
Yeah. Now we will move down. Yeah. This is very important. This chart is very important. Graphical representation. See what is given to you in this. Isothermal and free expansion for the ideal gas. Isothermal means what would be the situation in isothermal? Means temperature remains constant, right?
Yes.
Temperature would be constant. Now, for isothermal expansion of ideal gas into vacuum. If it would be vacuum, that time work done would be 0. Right? If there would be vacuum, there won't be any sort of change into temperature. There won't be any sort of change into volume. So what you will get the graph? You will get the graph in this manner. Okay? The slope would be in this way. This is a isothermal graphical representation. Here, pressure would be on the y-axis and volume would be on the x-axis. This is x-axis and this would be y-axis. And in this way, you will get the slope. Okay? When your temperature remains constant. So there would be the whatever change happened with respect to pressure and volume. What can you judge with this? With pressure, volume would be increases or decreases. If pressure increases, volume would be increases or decreases by looking at this graph.
Decreases.
Yes. If pressure increases, Yes,
Volume decreases.
volume decreases. Very good. And if volume increases, then pressure would decreases. Vice versa. Clear?
Yes, ma'am.
Yeah. So this would be the graph of what? Isothermal and free expansion of ideal gas when temperature remains constant. Graph would be represented in between pressure and volume. Pressure would be at y-axis. Volume would be at x-axis. And you will get the slope in this manner. Means if pressure is increases, what happened? Your volume goes on decreases. Clear? And vice versa. Fine. I hope you are noting down this.
Yes,
Are you
ma'am.
noting down this?
Yes, ma'am.
Fine. See now the next very important concept of your chapter, that is enthalpy. What is given on this? See about the enthalpy, what is given to you. What is enthalpy? It is defined as total heat contained of the system. Now total heat, how you're going to calculate? Total heat of system is nothing but what? Enthalpy. So how are you going to calculate the total heat? It is equal to sum of internal energy. Internal energy we represent with the help of what? U. Correct? And the pressure volume work done. Pressure volume work done is nothing but what? PV. Correct? Pressure volume work done, W is equal to PV. So your enthalpy H is equal to U plus PV. Okay? So what is the enthalpy? It is defined as the total heat contained in the system, not in a surrounding. System means the content which we are going to observe. Okay. And apart from that, whatever would be there around it, that is called as surrounding. Fine. So total heat content in the system is nothing but enthalpy. How are you going to calculate it? It is the sum of internal energy U and pressure volume work done, that is PV. So your enthalpy H is equal to U plus PV. It is mathematically represented in this manner. Now, how are you going to calculate the change in enthalpy? So change in enthalpy is heat absorbed or evolved by the system at constant pressure. So in this case, your pressure remains constant. Understand? Then you have to calculate the change in enthalpy. How are you going to calculate? You can calculate it at the constant pressure. Right? So delta H change means what? Initial enthalpy and the final enthalpy. From the final enthalpy, initial enthalpy need to be subtracted. So change in enthalpy is nothing but delta H, which is equal to QP. Means change into heat, final heat and the initial heat at a constant pressure. Understood? Yes or no? Okay. Now see, for exothermic reaction, what happened in exothermic? What do you mean by exothermic reaction? Heat would be evolved, right? Yes or no? Heat will be given off from the system. And for the endothermic reaction, heat would be absorbed in the system. So these two things you need to keep it in your mind. When exothermic reaction is there, system loses energy to the surrounding. Right? Suppose this is your beaker and this is your surrounding. So if heat is lost from this beaker, that time what we can say, this is exothermic reaction. Okay. And whenever exothermic reaction, system loses the heat to surrounding. And at this time, your change in enthalpy delta H is negative. Clear? And apart from that, if it would be reverse, suppose you're heating a beaker, you have to take a beaker in this, this is your system and this reaction is happening and you're supposed to heat this beaker with a burner. You're heating this beaker with a burner and this content would be get heated, temperature would be like this. Okay, so this reaction is what? Endothermic reaction. It absorbs the heat, right? And as it absorbs the heat, what happened? Your change in enthalpy would be positive. Because change in enthalpy is nothing but what? Final enthalpy minus initial enthalpy. If final heat would be more, means actually enthalpy is nothing but change into heat, right? If you're providing a temperature in endothermic reaction, your final temperature is more as compared to your initial temperature. So obviously the value which you will get, that would be positive. And if you go for the exothermic reaction, in this case, what happened? The system is already have certain temperature. When it loses the heat, that time temperature goes down. And when you do the subtraction, means the final temperature minus initial temperature, that time, as we know, heat is lost. So the value would be in negative terms. Clear? So in exothermic it is negative and in endothermic it is positive. Change in enthalpy. Clear?
Yes, ma'am.
Fine. Now we'll move forward.
Ma'am, in endothermic, it's positive, right?
Sorry.
In endothermic, it's positive, right?
Exothermic it is negative and in endothermic it is positive. In endothermic it absorbs the heat, right? And because of that temperature would be rise. Final temperature would be more than that of initial. And how you're gonna find out the change in enthalpy? Final minus initial. And that time you will get the value positive. Understood? Yes or no?
Yes, ma'am.
Yeah. See, endo means what? Your system absorbs the heat. Suppose you have your temperature first T1. The system has a T1 temperature. In endothermic, if you heat it, after a certain time period, it becomes T2. And we know that T2 is greater than T1, right? And when you have to calculate the delta H, that is the loss of heat or gain of heat. So here in this endothermic gain of heat is happened. So T2 minus T1. As we know that T2 is greater than T1, value would be positive. Clear? And when it would be exothermic, that time what happened? Your there would be the certain temperature T1 already. When it lose the heat, right? After certain time it become T2. In this case, T2 is less than T1. Correct? And hence the change in enthalpy delta H is equal to T2 minus T1. Hence it would be negative. Clear? Process would be same. Just the greater than the less than thing would be matter over here. In exothermic, your final temperature would be less, and in endothermic, your final temperature would be more. Because of that, positive and negative value you will get. Understood? Shall I erase?
Yes, ma'am.
Shall I erase?
Yes, ma'am. Yes, ma'am. You can.
Fine. We'll move down. Here it is given C. For exothermic reaction, system loses energy to the surrounding and hence delta H, QP both are negative. Delta H and QP means delta H is change in enthalpy, QP is what? Change in heat. Both are negative. And for the endothermic reaction, system absorbs energy from the surrounding and hence your change in enthalpy and change in heat. Both are positive. Clear?
Yes, ma'am.
Now see. Relation between delta H and delta U. What is the relation in between these two that we have to find? What is delta H? Change in enthalpy. What is delta U? Change in internal energy. These terms you should be known. If you don't know these terms, you won't understand what is delta H, what is delta U, everything would be bouncing over the head. Understand? And it should not be happening. So the basic term, its meaning, its representation, notation, that all things you need to be keep it in your mind. And hence, wherever possible, which you cannot keep it in your mind, you can note down somewhere. Right? So they have given us a general reaction. That is, A is a reactant, B is a product, and in a reaction, A is converted into B. Okay. Now, what they have said is, let HA be the enthalpy of reactant A and HB be the enthalpy of the product. Okay. What is the HA? It is enthalpy of reactant, right? And what would be the HB? It is enthalpy of product, right? Now, we know general formula H is equal to what? U plus PV, right? It is summation of the internal energy and the work done in pressure volume, correct? Yes or no? We have seen the definition of enthalpy, right? Now, our enthalpy of reactant would be what? HA is equal to UA, means internal energy of your reactant. Pressure would be constant. Okay, PVA. Because as we know that for the enthalpy, your pressure should be constant. Change in enthalpy you can calculate at the constant pressure. So VA may vary, volume may vary. So VA would be the volume for your reactant. The same thing you have to write it for the product. Enthalpy of the product would be HB, which is equal to UB plus PVB, where VB is nothing but the volume of your product. Clear? What do you mean by the delta H? It is what? Change in enthalpy, means your final enthalpy minus your initial enthalpy. Final enthalpy is the enthalpy of product. Initial enthalpy would be the enthalpy of reactant. Correct? Now these values, suppose this is equation 1, this is equation 2, and this is equation 3. So value of equation 1 and 2, you have to put it to the equation 3. What you will get? What you will get? Delta H is equal to, come on, tell me. Yes, Dhananjay, are you there?
Yes, ma'am, I'm there.
Yeah. So what you will get over here now? Delta H is equal to HB's value.
UB plus PVB minus UA minus
UB plus,
PVA.
yeah, PVB minus UA plus PVA. Correct?
Yes.
Yeah. Now what we're going to do? We are going to take these terms together. UB and UA, right? Subtraction sign would be there in that. That won't change. Correct? Yes or no? Can we do that?
Yes.
Yeah. So the previous things you understood, now these all. I can erase it.
Ma'am, once keep that equation, ma'am, I will note it.
Sorry?
That equations don't drop it, ma'am, I'll note it.
Okay, you want. Okay. See if you are writing still.
Yes, ma'am, 2 minutes system.
Yeah. Because after that, what we have to do, you have to take these terms closer. Means U terms would be together and P terms would be PVB and PVA terms would be together. That we have to take it together. Okay.
Yes, ma'am, done.
Okay. Now, shall I erase the previous these things?
Yes.
This one. Now check what you have to do with this. You're going to take this delta H is equal to UB minus UA. What I have done, I've taken this UB and this UA together and some minus sign would be in between. Correct? And this PVB and PVA terms I'm going to take into the another bracket. Okay? Yes, and as minus sign I already took into the bracket, I'm going to write it with a plus sign. Fine. Here what I'll get? PVB minus PVA. Right? So this is nothing but a change in internal energy. This is a final or product internal energy minus reactants internal energy. So what I will get over here? Delta delta U. U. So delta U plus, here in this 2, pressure is a constant that I'm going to take out. And here it is what? VB minus VA. This is nothing but a change in volume. So I will get delta H is equal to delta U plus P delta P. Clear? Yes?
Yes, ma'am.
Take it here. This is nothing but what? Change in enthalpy, final enthalpy minus initial enthalpy. Clear? HB minus HA. Fine. Now, a few things are there about the pressure as well that we have to put in this. What do you mean by the pressure extensive? Last time only for the ideal gas I gave you. P is equal to nRT, isn't it? P extensive is equal to what? nRT, isn't it?
Yes.
Remember or not? I hope you might have written somewhere. So
Yes,
check.
ma'am.
Yeah. So here, if P is equal to nRT, then for PVA, PV is equal to nRT, I guess. P extensive and V is equal to nRT. Correct? It was like that. So I will get what over here? PVA is equal to NA RT. This is for the reactant A. And then P BB is equal to what? It will be NB RT. This is for the product B. Now, what would be the change in this that you need to calculate? PVB minus PVA. You have this in your mind, like NB RT minus NA RT, correct? In this case, what you're going to do, this NB and NA, you're going to take it one bracket, NB minus NA. And as RT is a constant, it will be out of the bracket. R is a gas constant and T is a temperature, correct?
Yes.
Yeah. Yeah. So change in this NB minus NA would be what? Delta NG. That would be that change into this number of the reactant and the product molecules would be denoted by delta NG. And hence P delta V is equal to delta NG RT. And this value we are going to put into this equation. Whatever equation we got over here, in that we are going to put the value of P delta V. Here you just have to put the value delta NG RT. Clear? So what your equation becomes now? Shall I erase this? This one, PVA, nRT and all. Have you wrote?
Yes,
This
ma'am,
one.
you can erase it.
Okay. Now what you're gonna do? You'll just put this value of P delta V. You will get enthalpy delta H is equal to delta U plus P delta V. Instead of that, what you're gonna write? Delta NG RT. Clear? You can say this would be the equation number 4. This would be equation number 5. By putting the value of equation 5 in equation 4, you will get the equation number 6. Fine? Okay?
Yes, ma'am.
This expression is important. Clear?
Yes, ma'am.
Have you wrote? Shall I erase it?
Yes, ma'am, you can erase it. I was
Fine.
writing.
Now what you're going to do here? We are going to learn about the properties, extensive properties and intensive properties. What is that? I'll let you know. But before that, I just wanted to know whether you understood that expression or not. Yes.
Yes, ma'am.
Hello.
Yes, ma'am.
If you have any doubt, you can ask. Okay.
No, ma'am, no doubts. Sure, ma'am.
Now see, extensive property means what?
Ma'am,
It's
how
very simple.
numericals come based on that, ma'am?
Sorry.
Ma'am, will numericals come based on that?
Yes, yes. Numerical would be there on the base of that. Definitely, I'm going to start with numericals as well as earliest. Let me finish with the concept first. Once concept would be done, on the basis of that, whatever numericals would be asked into the previous examination, that we are going to solve together. Fine?
Okay.
Yeah. Extensive property means what? The extensive property is a property whose value depends on quantity or size. Okay, size of matter. What it should be? Quantity and the size of matter present in the system, where it should be present inside the system. So such a properties are called as what? Extensive property. Understand? What is the
Yes.
extensive property? Whose values are depend on quantity or a size of matter present in the system. Example is given like mass, volume, enthalpy. Everything is depending upon what? Quantity and the size of matter, amount of the matter present in the system in short. Okay. And what is the intensive property? Intensive property do not depend upon the size of the matter or a quantity of the matter present in the system. Correct? And example is temperature. It doesn't matter whether it is 1 kg or whether it is 1 gram. Its temperature melting point would be same. Boiling point would be same. Its density would be same. The pressure on it, it would be same. Isn't it? And such a qualities or such a what we can say properties are called as what? Intensive properties. Extensive property depending upon what? Size and the quantity of matter. Right? And intensive property does not depend upon the size and quantity of matter present in the system. These two, this is nothing but a difference in between both of this. And the next concept which you're supposed to learn, that is heat capacity. What is that? See here. See. The increase in temperature is proportional to the heat transfer. Right? Yes or no? Increase in temperature means what? Heat would be increases. If temperature increases, heat of the system also increases. Correct? Yes or no? So
Yes,
what
ma'am.
they said, increase in temperature is directly proportional to the heat transfer. Right? So if I have to write it in the proportional terms, how I'm going to write? Heat is equal to constant or coefficient into change in temperature. This would be the change in temperature, delta T. Okay, so I'll get it here, delta T. Change in temperature is directly proportional to the change in heat. Okay, or heat transfer. So heat transfer is nothing but constant into delta T. Right? This is about what? Proportionality law. Clear? This constant term is nothing but what? Coefficient, and that is denoted by C. So Q is equal to C delta T, and this C is called as what? Heat capacity. What does it called? Heat capacity. Understanding?
Yes.
What has been said? When temperature increases, your heat is also increases. So change in temperature is directly proportional to the transfer of heat. As delta T is directly proportional to Q. Correct? Because of that, Q is equal to constant into delta T. And this constant term is denoted by what? Capital C. And it is called as heat capacity. What does it call? Heat capacity. Clear?
Yes, ma'am.
Yeah. Now about this heat capacity, a few terms are given. Shall I erase it?
Yes, ma'am, you can erase it.
Yeah. Now see what is given about it. Heat capacity. In that, where coefficient C is called as the heat capacity, C is directly proportional to the amount of substance. Means your substance is more, your heat capacity is also more. C is directly proportional to the amount of substance. Okay. Now, here what they have given you, Cm is equal to C upon N. What does it mean? This is the heat capacity for 1 mole substance. Means total heat capacity divided by the number of moles. So you will get the heat capacity for 1 mole. So what do you mean by Cm? Cm is the heat capacity for 1 mole of substance. Where C is what? Total heat capacity. And N is what? Number of moles of that particular substance. So if you divide total heat capacity by total number of moles, you will get the Cm, that is heat capacity for 1 mole of the substance. Understood?
Yes, ma'am.
Yeah. Now the next is given, that is molar heat capacity. What is that? See? The molar heat capacity is defined as the quantity of heat required to raise a temperature of raise the temperature of the substance by 1 degree. Understand? It is defined as quantity of heat required to raise a temperature of substance by 1 degree. That would be in Kelvin or Celsius. It doesn't matter. Okay. So amount of heat required to raise the temperature of substance by 1 degree in Kelvin or Celsius is called as what? Molar heat capacity. And the specific heat capacity means what? It is defined as amount of heat required to raise the temperature of 1 unit mass of a substance by 1 degree. This is for what? This is for what? Quantity of heat required to raise the temperature of substance by 1 degree. They have not given how many units. Are they gave? No. So here you have to consider for the number of moles or mole of the 1 mole of the substance, we can say 1 mole of the substance temperature. If you raise by the 1 degree, either Kelvin and Celsius, that would be the molar heat capacity. But then when you raise the temperature by 1 degree of 1 unit mass of the substance, that is called as specific heat capacity. That 1 unit mass can be anything, maybe molecule, maybe atom, isn't it? 1 mole, 1 unit mass. 1 unit mass with respect to the substance is nothing but either atom or molecule, isn't it? Yeah?
Yes, ma'am.
Fine. So here, see what is specific heat capacity, what is given to you. Specific heat capacity is given to you in this way, see. That is Q, amount of heat required. This is your total heat capacity into M into delta T, where C is nothing but a total heat capacity, M is the mass of the substance, and delta is rising the temperature or changing the temperature. Okay? By that you are able to calculate the heat. Understood? This is the way by which you are able to calculate the specific heat capacity. Okay?